In 1995, the magnitude 7.2 Great Hanshin earthquake struck Japan. The kinetic energy released by the shifting fault lines ripped through the earth and decimated the port city of Kobe. The extreme violence of the seismic waves easily snapped steel highway reinforcements and pancaked modern mid-century concrete infrastructure in a matter of seconds. Yet just miles away in Kyoto, a remarkable architectural anomaly was observed amidst the urban destruction. The Toji Temple's 5-story wooden pagoda, standing nearly 55 meters tall and reconstructed in 1644, remained entirely unscathed by those exact same tectonic forces. This survival was not an isolated statistical anomaly. Historical archives spanning 1,400 years reveal that out of approximately 500 ancient wooden pagodas built across Japan, only 2 have ever collapsed due to an earthquake. The structural record demands an explanation. Without access to computer modeling, physics algorithms, or steel rebar, ancient Japanese carpenters engineered a structure capable of absorbing and dissipating seismic energy far better than 20th century high-rises. The resilience of the pagoda begins at the microscopic level, rooted in its primary building material, Chama cypress obtusa, or the Japanese hinoki cypress. Modern materials like concrete and steel begin to oxidize and degrade the moment they are cast or forged. Hinoki wood exhibits the opposite biological behavior. Its structural strength actually increases in the decades after it is harvested. Over its first 200 years, the cut wood reaches a long-term moisture equilibrium. This physical shift allows cellulose within its cellular structure to crystallize. After reaching this peak strength, the wood maintains its highly ordered structural integrity for a millennium, naturally fortified against rot and insect decay by its own botanical oils. Ancient builders designed colossal monuments using hinoki with the absolute confidence that the raw timber itself would outlast empires. Modern building codes mandate structures are tied continuously from foundation to roof. The Japanese pagoda utilizes the opposite approach, the pile of hats. Each story is stacked loosely on top of the one beneath, joined by intricate wooden joints, lacking any rigid metal fasteners. During an earthquake, this loose stacking allows each individual floor to oscillate independently out of phase. The structure effectively performs a snake dance, actively breaking up the harmonic resonance that typically shatters rigid buildings. To support the immense dead weight of the heavy clay tile roofs, the carpenters utilized Masugumi, complex interlocking wooden brackets. These decorative elements are highly efficient seismic dampers. They function by relying on Coulomb friction. As tectonic shaking intensifies, the lateral forces eventually exceed the static friction threshold of the wood. The tightly packed cubic blocks and projecting arms forcefully slip and slide against one another. This severe mechanical friction generates heat, safely bleeding off massive amounts of kinetic energy before that force can transfer into and snap the main load-bearing pillars. The structure is further stabilized by the balancing toy effect, a physical property generated by the exceptionally wide, heavy, overhanging eaves of the clay roof. By pushing immense mass far away from the building's central vertical axis, the eaves drastically increase the pagoda's rotational moment of inertia. When high-frequency jolts hit the foundation, the massive inertia forces the building to sway in a slow, graceful arc, rather than whipping violently. The final engineering component is the Shinbashira, a massive hinoki trunk running down the exact center. Observers assumed it was a load-bearing column, but it carries almost zero structural load. Later, it was suspended entirely from the upper floors, hovering inches above the earth. The Shinbashira functions as a giant free-moving pendulum and untuned mass damper. As an earthquake forces the loosely stacked outer floors to slide laterally, they cross the central cavity and physically slam into the heavy suspended pillar. Because the free-hanging Shinbashira oscillates at a completely different frequency than the outer shell, it usually sways left while the building sways right. These physical impacts actively counteract the momentum of the outer walls. The pagoda is a mechanical symphony of structural isolation, active friction damping, and pendulum impact. It operates entirely by yielding to the Earth's kinetic energy rather than opposing it. In 2004, the National Research Institute for Earth Science and Disaster Resilience put these ancient mechanics to an empirical test. They placed an exact 1/5 scale wooden pagoda on the E-Defense shake table and subjected it to 77 consecutive earthquake excitations. The model absorbed a simulated profile of the catastrophic 1995 Kobe earthquake and survived completely intact. The natural frequency isolated it from the shockwaves, and the wooden joints bled off the kinetic energy, validating centuries of architectural intuition. As modern skyscrapers reach new extremes in height, civil engineers are returning to these exact principles, reverse engineering the mechanics of the pagoda to build the megastructures of the 21st century. When designing the Tokyo Skytree, one of the tallest towers in the world, engineers explicitly modeled their solution on ancient wooden temples to handle extreme wind shear and seismic vulnerability. The tower relies on a colossal, structurally isolated concrete core, connected to the outer steel frame solely through flexible oil dampers. As the outer needle flexes, the inner core sways in opposition, reducing overall seismic strain by up to 50%. The exact same philosophy is currently driving the modern mass timber revolution. Advanced high-rises now utilize cross-laminated timber and friction-yielding joints, directly mirroring the sliding Masugumi brackets to safely dissipate structural stress. The survival of the Japanese pagoda demonstrates that true resilience in a volatile environment is not achieved through structural hubris or rigidity, but through the engineered capacity to flex, absorb, and yield.